Good day. I'm Ervin Baticos, ECE 3202 is about to tackle about capacitance of two-wire line. We conclude this chapter with the problem of two-wire line. The final configuration will consist of two parallel conducting cylinders of each circular cross-section, and we shall be able to find complete information about electric field intensity, the potential field, the surface charge density distribution, and capacitance. This arrangement is an important type of transmission line, as is the coaxial cable we have discussed several times before. We begin by investigating the potential field of two infinite line charges. In this figure, shows a positive line charge in the xz plane at x equals to a and a negative line charge at x equals to negative a. The potential of single line charge with zero reference at a radius of RO is Z equals to PL over 2 pi E ln RO over R. We now write the expression for the combined potential field in terms of the radial distance from the positive and negative lines R1 and respectively. The two parallel infinite line charges carrying opposite charges, the positive line is at xa, y equals to 0, and the negative line is x equals to negative a, y equals to 0. A general point P, axis x, y, 0 in the xy plane is radially distance r1 and r2 from the positive and negative lines, respectively. The equipotential surface are circular cylinders. Now, to solve, V equals to rho L over 2 pi E ln. We choose R10 as the RO of the R1 and R20 for the RO of the R2. We use the now PL over 2 pi equals to ln R10 over R1 minus ln R2 R20 over R2 is equals to ln R10 R2 over R20 R1. We choose R10 and equals to R20, thus placing the zero reference as at equal distance from each line. This surface is the x equals to 0 plane, expressing R1 and R2 in terms of x and ay. V equals to rho L, substituting the formula for R1 and R2, x plus a squared plus y squared over x minus a squared plus y squared, or equal to rho L over 4 pi E ln x plus a squared plus y squared over x minus a quantity squared plus y squared. In order to recognize the equipotential surface and adequately understand the problem we are going to solve, some algebraic manipulation are necessary. Choosing an equipotential surface V equals to V1, we define K1 as a dimensionless parameter that is function of the potential V1. K1 is equals to e to the 4 pi E V1 V sub 1 over rho L. So that K1 equals to x plus a quantity squared plus y squared over x minus a quantity squared plus y squared. After multiplying and collecting like powers, we obtain x squared equals minus a 2ax k sub 1 plus 1 over k sub 1 plus minus, 1 plus y squared plus a squared equals to 0. We next work through a couple of lines of algebra and complete the square. X minus a k sub 1 plus 1 over k sub 1 minus 1 squared plus y squared equals to 2a square root of 5 of k sub 1 over k sub 1 minus 1 quantity squared. This shows that the equals to V1 equipotential surface is independent of Z and intersects the xy plane in a circle of radius B. The given formula lately was equals to B. B equals to the formula 2a square root of k sub 1 over k sub 1 minus 1, which is centered at x equals to hy equals to 0, where h equals to a k sub 1 plus 1 over k sub 1 minus 1. Now let us attack a physical problem by considering a zero potential conducting plane located at x equals to 0 and conducting cylinder of radius b and potential dO v sub O with its axis located at distance h from the plane. We solve that the last two equations for a and k sub 1 in terms of dimension b and h. A is equals to square root of h squared minus b squared, and square root of k1 is equals to h plus square root of h squared minus b squared over b. But the potential of the cylinder is VO. So 53 leads to square root of k1 equals to e to the 2 pi e v sub O over rho L. Therefore, rho L is equals to 4 pi e v sub O over ln k1. Thus, given hb and v sub O, we may determine A and rho L and the parameter k sub 1. The capacitance between the cylinder and the plane is now available. For a length L in the z direction, we have C is equals to rho sub L times L over V sub O, or equals to 4 pi EL over ln k sub 1, or also 2 pi EL over ln square root of k sub 1. In other term, C is equals to 2 pi EL over ln h plus h squared minus b squared over b In short, 2 pi EL over cos negative 1 H over B. The heavy block circle. Now, the heavy block circle in figure 5.7, this figure shows the cross-section of the cylinder of 5-meter radius at a potential 100 in free space with its axis 13-meter distance from a plane of at zero potential. B equals to 5, H equals to 13, V sub O equals to 100, and we rapidly find the location of the equivalent line charge from A equals to square root of H squared minus B squared is equals to square root of 13 squared minus 5 squared equals to 12. Now, we will going to solve to find K sub 1. The value of the potential parameter K sub 1 from square root of K1 is equals to H plus square root of H squared minus B over B. Substitute 13 is equals to 13 plus 12 over 5 equals to 5. K sub 1 equals to 25. The strength of the equivalent line charge from the rho L 4 pi EVO over ln K1. We're going to substitute the given in this formula to find rho L. 4 pi times 8.854 times 10 to the negative 12 over cos 13 over 5 is equals to 34.6 picofarad over N. We may also identify the cylinder representing the 5-volt equipotential surface by hiding new values for K1, K sub 1, H, and B. We must first use K sub 1 is equals to e to the 4 pi E V sub 1 over rho L. Now, substitute the given E equals to 4 pi times 8.854 times 10 to the negative 12 times 100 over L times 50 over 3.46 times 10 to the 9. K1 is equals to 5. Then the new radius is B equals to 2A square root of K sub 1 over K sub 1 minus 1. Substituting the formula, 2 times 12 square root of 5 over 5 minus 1. Then B equals to 13.42 meters. And the corresponding value of H becomes, from the formula, H equals to A K sub 1 plus 1 K sub 1 minus over K sub 1 plus 1 over K sub 1 minus 1 is equals to Substituting the given 12 times 5 plus 1 over 5 minus 1, then h equals to 18 meters. This cylinder is shown in the figure. In this figure, the electric field intensity can be found by taking the gradient of the potential field by the given E is equals to rho L over 4 pi E ln x plus a squared plus y squared over x minus a squared plus y squared. Thus, E is equals to rho L over 4 pi E is multiplied by 2 times x plus a squared plus 2y over x plus a squared plus y squared, and 2 times x minus a ax plus ya ay over x minus a squared plus y squared. If the value dx at x equals to h minus b and y equals to 0, we may obtain the value of p s max by the formula negative dx or equal to rho L 2 pi h might multiply by h minus b plus a over h minus b plus a quantity squared minus h minus b minus a over h minus b minus a squared. PS is equals to 3.46, substituting the formula, times 10 to the negative 9 over 2 pi 13 plus 5 plus 12 over 30 squared minus 13 plus 5 minus 12 6 squared is equals to PS 0.0734 nano over per meter squared, and the P max is equals to 2.25 PS min. The capacitance between the two circular conductors separated by a distance 2h is 1/2 the capacitance given. The last answer is of interest because it's given as an expression for the capacitance of a section of two-wire transmission line, one of the types of transmission line studied later in chapter 12. Thank you.